All right, so what we're starting today is our next unit. This is Unit 2A, and here we're going to be talking about some of the basics of chemistry. First of all, if you're wondering why are the units always broken down A and B, it's not always that way. That's just a way of keeping the content kind of manageable, because if we kept all the stuff that was related in Unit 2, then we'd be basically spending 4 weeks on a unit, and then the test would be massive. So this is actually to help break things down into manageable chunks. And then the other question is, why are we going to be talking about chemistry? This is biology class. Well, the fact of the matter is that in order to understand biology at the cellular level, okay, because the cell being the smallest unit of biology, we have to understand the chemistry going on inside of that. Okay, so we have to be understanding biology at the molecular level. So we have to know a little bit of chemistry in order to kind of move forward in biology. So we're going to take a little bit of time to kind of break that down. And then in Unit 2B, we're going to talk specifically about the substances that make up living things. And that, of course, talk about the molecules that make up those living things. So Unit 2A right here, we're kind of setting up the information that we need to understand in order to make sense of biology later on, not just in the next unit, but in the rest of the year. So here, our new priority standard for this particular unit, the student will interpret formula representations of molecules and compounds in terms of composition and structure, and in the specific case of water, discuss the special properties of water that contribute to Earth's suitability as an environment for life. So essentially what this is talking about is we need to understand how chemistry impacts life. Okay, the chemicals, the compounds that make up living things, and then very specifically talking about how water is very important to life on this planet. I will point out that some of this stuff will hopefully be familiar, because I know you've talked about atoms and molecules prior to this class. Probably, I think, 6th grade, you talked about that a little bit. We will, of course, be talking about chemistry in the context of biology. That is, how does this impact life? So to start off here, hundreds of years ago, there were a bunch of Greek philosophers that were sitting around and basically thinking about what it means to know stuff. So remember, science is about gathering knowledge. So in addition to being philosophers, they were indeed scientists as well. So they were interested in acquiring knowledge. And some of these scientists, philosophers, sat around and said, okay, well, what if we have a thing? Let's say we have an apple. Okay, so you have this apple, and let's cut it in half with a knife. Okay, what do you have? Well, you have two halves of an apple, right? So both half still looks like an apple. It still smells like an apple, still tastes like an apple. So by cutting it in half, we haven't changed that apple into anything other than a smaller apple. So what if we take one of those halves and cut it in half? Now we have a fourth of an apple. Okay, again, still smells, still tastes, still looks like an apple, just cut into smaller pieces. So the question was, okay, imagine we had a knife. It was sharp enough that we could just keep on cutting that apple in half, and then those halves in half, and half, and half, and half, and half, and half. So you cut a fourth into half, you get an eighth of an apple. Then you cut that eighth in half, you get a 16th. Cut that 16th in half, you get a 32nd. Cut that in half, you get a 1/64th. And so imagine you just kept on cutting that in half, and half, and half, and half. And the question was, how far can we cut that apple and still have an apple? How far can we cut it and still have something that has the characteristics, the properties of an apple? And at what point can we cut that substance into small enough pieces that we break it down into the stuff that makes up the apple itself? So at the time, these Greek philosophers didn't quite know what to make of this idea. And what they imagined were there were these fundamental particles that made up the universe, everything. And they called these particles atmos, which is the ancient Greek word for air. And we use that root word today to describe the atmosphere, that is the air that surrounds our planet. But they use the word atmos to describe these things, these particles that must be the substance that makes up all matter. Okay? So what they were thinking about is how far can we cut something down and get to the fundamental building blocks of matter itself. So we describe that today as the elements. The elements are substances that cannot be broken down into anything simpler. So the elements are the building blocks of the substances that make up all things. And the smallest unit of an element is the atom. That term atom comes from that Greek word atmos. So the atom is the smallest unit of matter, much the same way we talk about in biology that the cell is the smallest unit of life. Okay? So the atom is comparable in terms of basically being the smallest, simplest unit of this science. So the first question that we have here is, which of the following would be considered an element? Okay, so we have water, which we know is H2O, sugar, which is C6H12O6, oxygen gas, which is O2, or ammonia, which is NH3. So which one of those substances would be considered an element? Okay, the correct answer here is C, oxygen gas. Why is oxygen gas an element? It's only made out of one thing. So H2O, water. Water is very simple, yes, but it's made out of two things. The H is for hydrogen and the O is for oxygen. So we can actually split a water molecule into simpler things, into just hydrogen and just oxygen. Okay. Sugar and ammonia are bigger and more complex. We have more stuff going on there. But oxygen gas, the air we breathe, is just O2. It's two oxygen atoms together. Okay, so if we cut that oxygen gas in half, we still just have oxygen. Okay, so this is what we mean by an element. It is the simplest that we can make something without breaking it down any further. Okay, we can't break oxygen down into anything simpler than just oxygen. So the smallest particle of matter is the atom. And the next logical question, if you continue this Greek line of thinking, is, okay, if we cut an apple down in half and half and half and half and get down to the atoms, well, what would happen if we cut an atom apart? So the building blocks of the atoms are what we call subatomic particles. The prefix sub means below. So subatomic is below the atom. So what is the particle that is below or smaller than an atom? And you're probably familiar with these. Okay, these are the protons, the neutrons, and the electrons. These are the building blocks of the atoms. Now, when we talk about an atom, we say, okay, that atom is the smallest unit of an element. So let's say we have oxygen, for example. Oxygen is the air we breathe. So if I take an oxygen atom and chop it down to just the subatomic particles, it is no longer oxygen, meaning that it is no longer the substance that we can use to breathe. Okay? It loses the properties. It loses the characteristics that makes it useful for breathing. Okay? So the particles that make up these atoms are kind of universal. It's how we put those particles together that makes each element unique. And then each element has its own special characteristics that are different from all the other elements. Okay? So when we look at an atom, okay, the majority of the atom's mass, 99.9% of its mass, is found in the center in what we call the nucleus. Okay? So the majority of the mass of the atom is found in the center. Okay? And within that nucleus, we find two of our three subatomic particles, the protons and the neutrons. Okay? If we were to take an atom and blow it up to the size of, say, a football stadium. So if you've ever seen the Buccaneers play in person, they play at Raymond James Stadium. Okay? If you imagine the size of a football stadium, okay, if an atom was the size of a football stadium, the mass of that atom would be in the center of that stadium. And it would be about the size of a marble sitting on the 50-yard line. So even though the mass of the atom is in the center, the atom itself is a lot of empty space. Okay? So this is something that's kind of hard to wrap your brain around. And this is what makes the science of chemistry a little bit more difficult than some other sciences, because we're dealing with objects that even with our most powerful microscopes, we have a hard time visualizing. So a lot of this is stuff you have to kind of imagine in your head. Two particles that are found in the nucleus are your protons and your neutrons. Protons have a positive charge, so think about protons, positive, both start with P. And then neutrons have no charge. Neutrons are what we describe as neutral. Okay, so think of neutron neutral. Now, when measuring the mass of an atom, measuring in units like grams is not very convenient, because a single proton would be 0.000000. We'd have to say zero for a very long time to get to the mass of an atom in grams. Okay, so it's not very convenient to measure it that way. So what scientists instead do is they measure the mass of a proton using what they call atomic mass units, or AMUs for short. So they say, okay, one proton weighs 1 AMU. A neutron also is equal to 1 AMU. So the mass of an atom is measured in the total number of protons and the total number of neutrons found in the nucleus of that atom. And you're going to get what is called a mass number, which is measured in AMUs. The third type of subatomic particle is the electron. The electron is found on the outside of the nucleus. So electrons are zooming around the outside of the nucleus. And electrons have a negative charge. The movement of electrons is what we call electricity. So you plug something into the wall socket, what's powering that electrical device, like a blender or whatever, is the flow of electrons. The movement of electrons is electricity. Okay. Electrons are in constant motion, and these electrons are zooming around the nucleus. And we describe the path that they follow in orbitals. Now, when you see a diagram of an atom, you usually see the nucleus in the center and then these nice rings of electrons going around the outside. This is sometimes referred to as the planetary model, kind of like how the sun is in the center of our solar system and the planets go around the sun. Unless you're a flat earther, then I have no idea what to do with you. But the electrons also zoom around the nucleus, much like the planets orbit the sun. However, electrons do not follow nice, neat paths the way the planets do. Electrons, the way I like to describe them is that they're kind of like hyperactive kindergartners that we have just fed sugar and Mountain Dew. Okay, so imagine you have a hyperactive kindergartner, and then you give them a bunch of sugar, like candy and Mountain Dew, and then just like release them into the classroom. Okay, they're going to be all over the place. Kindergartners have a hard time keeping still to begin with. Load them up with sugar, they're going to be bouncing off the walls. This is how electrons are. Electrons are in constant motion. They're constantly zooming around, but they can't follow a simple path. They're going to be all over the place. So basically what we find is an atom has a region, a zone around it where the electrons are located, and we call that the electron cloud. Okay? So imagine you're the teacher in a kindergarten classroom, and you've just fed cookies and Mountain Dew to all your students, and we take them out to recess. Okay, so yes, you'd be crazy to do that, but as the teacher, you stand in the middle of the playground. So what's going to happen? You're going to have just kindergartners running around all over the place. They're going to be on the swings and their monkey bars and just like bouncing off the walls. Okay, this is how the electrons are. But something you might know about kindergartners is that they're drawn to teacher. There's always a kindergartner pulling on teacher's shirt going, teacher, 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 look at this cool rock that I found. Teacher, oh, I hurt my elbow. Teacher, teacher. Okay, so there's always kindergartners zooming around, but they're always drawn to where the teacher is. So this is how the atom is set up. The nucleus in the center, okay, that's where all those electrons want to go, but they can't sit still long enough to stay there. So they're constantly zooming around, getting near where the nucleus is, but they then zoom away. So something important to remember about atoms in general is that, and just the natural forces in the universe, is that positive charges attract negative charges. So positively charged protons are going to be drawn to negatively charged electrons. And negatively charged electrons are going to be drawn to those positively charged protons. So just like how those kindergartners are drawn towards the teacher, they always got to talk to teacher, always got to show teacher this cool lizard I found. Okay, the electrons are constantly zooming towards the nucleus. They just can't sit still long enough to actually stay in the nucleus. Okay. So it's important to know that opposite charges attract. And you hear the phrase opposites attract all the time. In the case of protons and electrons, that is exactly true. Now, the opposite of that is that if you have two like charges, that if you have two positively charged protons or two negatively charged electrons, like charges repel each other. They're going to push away from each other. Okay, so if you have two kindergartners get too close, they're going to bounce off of each other and go flying in the opposite directions. Okay, so electrons don't like to be near other electrons. Protons don't like being near other protons. Now, when measuring the mass of an atom, we count the number of protons and the number of neutrons in the nucleus. What about the mass of the electrons? So we don't count the mass of electrons for a couple reasons. First of all, electrons are very, very light compared to protons and neutrons. They measure to be about 1,836th the mass of a proton. Now, how do we know that number? Well, some very smart science nerds figured it out, and I'm not going to bother trying to explain how because I don't quite understand it myself. But we know that electrons are extremely small compared to a proton. Okay, so even if you had the biggest atom we know of, the biggest atom we know of has 118 protons in it. That would draw in 118 electrons, okay, because positive charges draw in those negative charges. So even if you had over 100 electrons, that would barely be a tenth of the mass of a proton. So for all intents and purposes, we can ignore electrons. They weigh so little that we don't have to worry about them. But the other reason why we don't have to worry about the mass of electrons is because electrons don't necessarily stick to the same atom. Okay? So imagine your hyperactive kindergartners. One kindergartner just makes a bolt for the gate, jumps over the fence, and just goes running down the street. Okay? So that electron is gone. Okay? We're just going to wave goodbye. We didn't like that kid anyways. Okay? So electrons aren't necessarily stuck to the same atom. So they can move in and out of atoms. So sometimes you can't even keep track of how many electrons are there, let alone how much mass they're contributing to the mass of the atom. So when we have an atom, you have the positively charged protons in the middle and the negatively charged electrons on the outside. They're being drawn to each other. So the negative charges of the electrons and the positive charges of the protons basically cancel each other out. So if you have an equal number of positive charges and an equal number of negative charges, an atom is then going to be described as neutral. Okay. This is what is known as electronegativity. This is one of the fundamental forces in the universe. Positive charges and negative charges, when those are balanced, we are neutral. Okay. So say, for example, we have an atom of oxygen. Oxygen has 8 protons and generally has 8 neutrons. And then we'll generally have 8 electrons as well, because the 8 positively charged protons are going to draw in 8 negatively charged electrons. And that's going to create a neutral oxygen atom. Now, it's important to note that all oxygen atoms have 8 protons. Okay, this does not change. And this is what makes oxygen unique from all the other elements, is because of the number of protons found in its nucleus. Now, next formative question, true or false? Since the neutron has no charge, it serves no purpose in the atom. Of course, it stands to reason if there are neutrons inside of an atom, that neutron has some purpose. Okay, even if it's not electrically charged, there's a reason to have those neutrons. And the answer comes back to that idea that like charges repel each other. So if we have a bunch of positively charged protons in the nucleus of an atom, those positively charged protons don't want to stay there. Okay, so those protons are going to try to push away from each other. So how do we keep those protons in the nucleus? We have to glue them together. Okay, and that's what neutrons are. It's kind of atomic glue. Okay, the neutrons hold the protons in place. Now, if you have a really big atom with lots of protons, you're going to need a lot of glue to hold those protons together. And in some atoms, there's just not enough glue. So if you have something like uranium, uranium has lots of protons in it. And if you don't have enough neutrons, that uranium nucleus tries to fall apart. Okay? And when a nucleus falls apart, that is what we call a nuclear reaction. And uranium is kind of famous for being unstable like that. And all it takes is just kind of bonking a bunch of uranium atoms together to get those nuclei to break apart, and we get a nuclear reaction. This is what happens in a nuclear reactor, or worse, a nuclear explosion. So if you have like an atomic bomb, what you're essentially doing is releasing the energy that's found within the nucleus. And there's a tremendous amount of energy in that nucleus. Even very small nuclei has a lot of energy in there. If we can break those apart, we can release that energy and blow stuff up really well, or we can use it to power an electrical plant and send power to homes. And that's what a nuclear power plant does, is it uses that energy that's contained in the nucleus and powers the generators. Okay. So in order to understand atoms a little bit better, we kind of simplify the way that they are. We know that these atoms are these dense nuclei with this cloud of electrons zooming around. And that's kind of hard to visualize. So a scientist by the name of Niels Bohr came along and said, you know what? Here's a simple diagram we can use to better understand atoms. And this is what we call the Bohr model. Okay, so the Bohr model here we have in the center, it says 8n and 8p. That's 8 neutrons and 8 protons. Okay, and then we have rings surrounding that. Those rings represent the electrons. Okay. Now, we know that electrons don't orbit in nice, neat little patterns, but this is just a simplified way of looking at the atom so we can better understand how that atom is put together. Okay. So the information in the Bohr model is reflected on the information that we have on the periodic table of elements. Okay, so you've probably seen the periodic table of elements before. There's one in your agenda. And this is basically a list of all the known elements. Okay, and on that periodic table, there's going to be a certain amount of information for each element. So here we have the entry for oxygen. So we have 4 things in that box. You have a number at the top, you have an abbreviation, then the name, and then another number at the bottom. The number at the top, okay, in this case, number 8. This is the atomic number, and the atomic number is equal to the number of protons in an atom. So oxygen is number 8 on the periodic table because all oxygen atoms have 8 protons in its nucleus. If we have any more or any less, we are not dealing with oxygen. Okay, so if we have 7 protons, that's not an atom of oxygen, that's an atom of nitrogen. If I have 8 protons, I can breathe just fine. If I have 7 protons, I'm going to suffocate to death because you can breathe as much nitrogen as you want. It's not going to keep you alive. Okay, same thing. If I have 9 protons, that's not oxygen anymore. That's a gas called fluorine. If you inhale a lung full of fluorine, it will kill you dead. Okay, because fluorine is highly reactive and it will literally shred the tissues of your lungs apart. Okay, so you want just oxygen, 8 protons, no more, no less, because that's what your body is going to use to keep you alive. The letters that are found inside the periodic table, those are the standard abbreviations for each element. Now, those standard abbreviations are universal across language. So regardless of what language you speak, you're going to use these same symbols. These are international. Now, what we call an element changes from language to language. So in English, we call it oxygen. In other languages, we use different words, but we're always going to use the letter O to represent oxygen for that chemical symbol. Now, some chemical symbols have 2 letters. The first letter is always capitalized. The second letter is always lowercase. Okay. The chemical symbol for hydrogen is capital H. The chemical symbol for helium, since H is already being used, is HE, capital H, lowercase e. The other number that's listed in the periodic table, this is the atomic mass number, or the mass number. And notice that this is some fraction, so 15.999. So remember we said the mass of an atom is the total number of protons and the total number of neutrons. So where does this fraction come from? Well, this is taking into account that not all oxygen atoms have the same number of neutrons. They have to have the same number of protons, but they can have different number of neutrons. So some oxygen atoms, most oxygen atoms, have 8 neutrons. Some only have 7. And there are some that actually have 9. So imagine you're gluing something together. Sometimes we can use lots of glue. Sometimes we can use very little glue, but we could still hold it together. Okay, so what that 15.999 represents is the average number of the mass of an oxygen atom. So if we were just to pluck any random oxygen atom out of the air, it would on average have a mass of 15.999. Okay. Now, if you wanted to know the average number of neutrons in an atom, what you can do is take that mass number and round it to the nearest whole number. So 15.999 obviously would round to 16. Okay, so if we have a mass of 16, and we know that 8 of that mass has to be protons, because that's how many protons that all oxygen atoms are going to have. So 16 minus 8 is going to give us a remainder of 8 mass, and that's going to be your neutrons. So 8 protons plus 8 neutrons are going to give you 16 total mass. Now when we look at the Bohr model and we look at the rings that are going around that Bohr model, so we have accounted for the protons and the neutrons, so those rings are going to account for the electrons. Now, something that Bohr figured out, and also other scientists kind of contributed to this idea, is even though the electrons are zooming around in kind of random patterns, they do have a tendency to try to get as close to the nucleus as they can. But because electrons push other electrons away, they tend to end up in kind of zones around the nucleus. So some electrons get really close, and then some electrons get as close as they can without getting too close to those first set of electrons, and then further and further and further away. So this creates what we call the orbitals. These are sometimes called electron shells. Okay? But the orbitals represent how many electrons can fit close to the atom close to the nucleus, and then further and further away. So in the first orbital, we can hold 2 electrons. So we have 2 electrons can get really close to that nucleus, but they take up that space. So any additional electrons have to go into the next orbital out. Okay, so the second orbital can hold up to 8 electrons, okay, before we have a full orbital. Okay, but oxygen only needs 8 electrons because it has 8 positively charged protons bringing in 8 electrons. So the first 2 electrons are going to fill that first orbital. The next remaining 6 electrons are going to fill that next orbital. Okay, even though that orbital is not complete, it doesn't have 8 total, that's how many electrons that oxygen atom is going to have. Okay, so the reason why we point all this out is because this becomes important on how atoms interact with each other. We'll get into that in the next section. But the Bohr model, even though it's not a true representation of what the atom looks like, is a very convenient way of describing the structure of the atom. All right, so last formative question. Sodium, which the entry in the periodic table is noted above, has an atomic number of 11 and a mass number of 22.990. How many protons does sodium have? Is it A, 22.990, B, 12, C, 33.990, or D, 11? Sodium is number 11 on the periodic table, so it has 11 protons. Okay. This is how the periodic table of elements is put together. It is a list of elements that we know of from smallest to biggest. Okay, and the number of each element represents its number of protons. Okay, the number of protons that an atom has changes its characteristics. So each element is unique, and what makes it unique is the number of protons it contains. So this is the periodic table of elements. And you'll notice that the periodic table has a particular shape to it, and this is because it was invented by a guy named Mendeleev. And Mendeleev arranged the periodic table in a very particular way. And when you look at the periodic table, it looks like just a chart, but in reality, it is pure genius. And I say this, and people roll their eyes at me and say, Mr. Wassman, you're just being a big science nerd. But if you know how to read the periodic table, it gives you so much information that can be useful for doing the science of chemistry. Luckily, we won't need to get too far into it, but it's good to appreciate how the periodic table is put together. So first of all, the periodic table is divided into vertical columns and horizontal rows. So the horizontal rows going across, those are called the periods. Okay, this is why it's called the periodic table of elements. There are 7 periods, okay, going from top to bottom. Okay, so the period that I have highlighted here, okay, if you notice, all the elements in that row are going in sequential order, adding a proton each one. So number 19 is potassium. Okay, that is the atom, the element that has 19 protons in its nucleus. Number 20 is calcium. That has 20 protons. 21 is scantium. That has 21 protons, and so on. So all the elements in one row going across, these are increasing number of protons. The vertical columns are what we call groups or families. Depending on which source you look at, group is usually used by chemists. Family is often used by non-chemists because all the elements that are in that same vertical column have similar characteristics. They're not the same, but they have some characteristics in common. Okay, so think about like a family, moms, dads, sons, daughters. They often have similar characteristics. They might have the same hair color, similar eye color, might be similar of height. Okay, so they have a lot of things in common because they're family. Okay, but each member of that family is unique. They all have their own unique personalities, hobbies, whatever, and some will have strange characteristics. So you'll have a family with all brown hair and then have one child with red hair. Okay, so that's kind of how the families of the elements are. All these elements are similar in many ways, but they are all unique. Okay, so no two elements are exactly the same. When we look at the intersection of a period and a family, we have a single element. So here we have number 32, which is germanium. Okay, and again, like in biology, if you discover something new in chemistry, you get to be the one to name it. Okay, so a lot of these elements are named after various things. Some are named after a place, like germanium is named after Germany, where the element was discovered. Some are named after people, like if you look at number 99, that is Einsteinium. That, of course, was named after Albert Einstein. Some are named after properties of the element. So it just depends on what that scientist was thinking when they discovered this element and said, okay, this is how we're going to describe it. Germanium, if we look, it is number 32 on the periodic table. So that means it has how many protons? 32. Before that is number 31. That's gallium. After that is number 33. That's arsenic. So in that row, we see sequentially the number of protons in the elements. Now, something else that a chemist understands is as we are going across that row, we're also going to be seeing increasing size of the nucleus, but decreasing size of the electron cloud. And this is due to the fact that the more protons you have in those orbitals, the closer those electrons are going to be kind of drawn in. So there's something to be said about the size of an atom by looking at the periodic table. Then if you look at that vertical column, germanium is in the same column as carbon, silicon, tin, lead, and then the last one, I can't read that name. So all of these elements react in similar ways. For example, all these elements react with hydrogen in a very particular way. So they are very similar in that respect. Okay. Now, something that you might notice about the periodic table is when you look at the symbols that we use, they don't always match the names. So, like, for example, potassium, number 19, has a chemical symbol K. And now, there's not a K in the word potassium, so where did that come from? Well, some of the symbols come from the older words that they use to describe these elements. Like iron is Fe, that's number 26 on the periodic table. Why did they use Fe? Well, because iron used to be known as ferium. So ferium is the ancient word for iron. Iron is the English word that we use today to describe that metal, that element. Okay, so sometimes the elemental symbols don't necessarily match the names, and that's why. It's because it's coming from a different language or an ancient word for that element.